This video is the submission on behalf of the University of Calgary Drillbotics team for the 2019 competition. This video presentation will serve to outline our Phase 1 design proposal. This year's design has been modified to accomplish directional drilling in a safe and reliable manner while being compliant with all new Drillbotics guidelines. One of the major changes to this year's design include a new push-the-bit style bottom hole assembly, a rotating flex shaft that runs through a flexible stationary outer sleeve will provide power to the bit. An actuator near the drill bit will provide force that will push the bit and accomplish the desired directional drill trajectory. The outer sleeve of the bottom hole assembly will be keyed and fit into a groove on a new custom-designed wellhead that will limit azimuthal deviation. Another major improvement to this year's rig is a rock stabilizing design that will secure the rock, wellhead, and rig frame together as one cohesive unit. The drilling fluid for this year's competition has also been changed to air, with a new air drilling system designed to accommodate this change. Other changes include a new drill pipe stabilizer, new threaded drill pipe connection, new mast design, and the addition of a spring to the drawworks for more sensitive weight on bit adjustments. These are just some of the new and exciting changes we have planned for our 2019 design.
Next, moving on to the electrical side. The control system will utilize a Simulink real-time system to allow for communication between the sensors and computer systems. This system will aim to optimize the rate of penetration while maintaining the directional trajectory of the drill bit by adjusting drilling parameters such as weight on bit and the top drive rotary speed. A wireless analog gyroscope sensor will be placed 1 inch from the drill bit to reduce input lag. The sensor will send data to the surface via Bluetooth technology. The housing will be made of either Teflon or another plastic material, as Bluetooth signals do not pass through metal. This sensor will measure the deviation of the drill bit in the X, Y, and Z directions, which will create a drilling trajectory diagram in the user GUI. An analog accelerometer will also be positioned on the upper end of the drill string to monitor and record vibrations resulting from varying rotary speeds in the drill string. The weight on bit will be read from a load cell sensor that is positioned between the top drive and stepper motor chain, which measures the tensional and compressional forces during the drilling operation. A spring attached to the chain will allow for incremental control of weight on bit using the stepper motor. An optical encoder measures the relative position of the drill bit from the rig floor to determine a rate of penetration. The control system will also include various safety parameters, such as the use of LED lights to indicate active drilling components, as well as a frame-mounted limit switch that prevents the drill bit from exceeding a preset measured depth, which essentially acts as a soft shutdown mechanism. The accelerometer will also prevent the top drive from assigning rotary speeds that will result in dangerous levels of vibrations, which will be determined through a period of testing. The proposed control system starts by increasing the weight on bit past the starting threshold to start drilling, after which this weight on bit will be increased and the rate of penetration measured again. As long as the rate of penetration increases after each increase of weight on bit, this will continue until the rate of penetration no longer increases, at which point the founder's point will have been found. This will indicate the optimum value for the weight on bit, which will be used for the remainder of the drilling process, and rigorous testing will be done to find the optimal starting point for weight on bit. That concludes this presentation. Thank you for your consideration of our submission into the 2019 Drillbotics competition.